What if I told you that somewhere in the darkness beyond Neptune, something massive is lurking? Something so enormous that it's bending the fabric of our solar system, yet we've never actually seen it. This isn't science fiction. This is Planet 9, and it might be the most important astronomical discovery of the 21st century, hiding in plain sight at the edge of everything we know. So, welcome back to the channel. Today we're diving deep into one of the greatest mysteries in modern astronomy. We're talking about a planet that may or may not exist, a world that could be 10 times the mass of Earth, orbiting in the frozen darkness billions of miles from the Sun. And the craziest part? We have compelling evidence it's out there, even though no telescope has ever captured its image. Before we go any further, make sure you hit that subscribe button and turn on notifications, because we're about to embark on a journey to the outer reaches of our solar system, where reality becomes stranger than fiction. This is going to be a long video, so grab your favorite drink, get comfortable, and let's explore the mystery of Planet 9 together. To understand why Planet 9 is such a big deal, we need to talk about what we thought we knew about our solar system. For most of human history, we believed we had it all figured out. The ancient astronomers knew about Mercury, Venus, Mars, Jupiter, and Saturn. These were the wanderers, the planets visible to the naked eye, moving against the fixed backdrop of stars. Then came the age of telescopes, and everything changed. In 1781, William Herschel discovered Uranus, doubling the known size of our solar system overnight. It was a shocking revelation. If there was one planet we'd missed for thousands of years, what else was out there? The discovery of Neptune in 1846 was even more remarkable. Astronomers noticed that Uranus wasn't moving quite the way it should. Its orbit had strange wobbles, irregularities that couldn't be explained by the gravitational influence of the known planets. Two mathematicians, Urbain Le Verrier in France and John Couch Adams in England, independently calculated that these wobbles must be caused by another planet, one we hadn't discovered yet. They predicted where this planet should be. Astronomers pointed their telescopes at that spot, and there it was. Neptune, a planet discovered not by seeing it first, but by calculating it must exist based on its gravitational effects on other objects. This discovery was revolutionary. It proved that mathematics and physics could reveal hidden truths about the universe. It showed that we could find objects in space, not by looking for them directly, but by studying how they affect their surroundings. This method, this detective work using gravity as a clue, would become crucial to our story. For about a century after Neptune's discovery, astronomers thought the solar system was complete. Sure, Pluto was discovered in 1930 by Clyde Tombaugh, and for decades it was considered the 9th planet. But as we learned more about Pluto, we realized it was much smaller than we thought. And it wasn't alone out there. The Kuiper Belt, a region of icy objects beyond Neptune, turned out to be full of Pluto-like worlds. In 2006, the International Astronomical Union made the controversial decision to reclassify Pluto as a dwarf planet, reducing our solar system back to 8 planets. Most people thought that was the end of the story. 8 planets, some dwarf planets, the asteroid belt, the Kuiper Belt, and the distant Oort cloud of comets. Our solar system was mapped, cataloged, and understood. We had it all figured out. But we were wrong. In the early 2000s, astronomers started noticing something weird. As telescope technology improved and surveys of the outer solar system became more detailed, researchers began discovering extremely distant objects, way beyond Neptune in what we call the scattered disk and the detached region of the Kuiper Belt. These objects, sometimes called trans-Neptunian objects or TNOs, have incredibly elliptical orbits that take them far from the Sun and then bring them relatively closer in a long, stretched-out path. Some of these objects take thousands of years to complete a single orbit. They're incredibly faint, incredibly distant, and incredibly difficult to study. But here's where it gets interesting. In 2003, astronomers discovered an object called Sedna. Sedna is weird, even by the standards of distant solar system objects. Its orbit is so elliptical and so distant that at its closest approach to the Sun, it's still farther away than most Kuiper Belt objects at their most distant point. At its farthest point, Sedna is about 937 astronomical units from the Sun. To put that in perspective, 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Sedna gets 937 times farther than that. The discovery of Sedna raised a lot of questions. How did it get into such a strange orbit? Neptune's gravity couldn't explain it. In fact, Sedna's orbit seemed to be almost completely unaffected by any of the known planets. Some astronomers suggested that maybe a passing star had pulled Sedna into this orbit billions of years ago, back when the solar system was young and more crowded. Others suggested that maybe the Sun had a distant binary companion, another star that influenced these orbits. But these explanations seemed like stretches. Then came more discoveries. In 2014, astronomers Chad Trujillo and Scott Shepard discovered another object with a strange orbit, designated 2012 VP113. In their paper announcing the discovery, they noted something fascinating. This object, along with Sedna and a few others, all seem to have their most distant points, called their perihelia, clustering in a similar direction in space. The orbits were aligned in a way that seemed too coincidental to be random. Think about it like this. Imagine you have a bunch of ice skaters all going around an oval rink, but they're all leaning to one side at the same time. That's not what you'd expect from random motion. Something must be pushing them or pulling them in that direction. Trujillo and Shepard suggested that maybe, just maybe, there was another planet out there, a super-Earth perhaps, shepherding these objects into aligned orbits through its gravitational influence. But at the time it was just a suggestion, an interesting idea that needed more evidence. That evidence was about to arrive in a big way. In January 2016, 2 astronomers from Caltech, Konstantin Batygin and Michael Brown, dropped a bombshell on the astronomical community. They published a paper in the Astronomical Journal with a bold claim. Based on detailed computer simulations and statistical analysis, they argued that there was strong evidence for a 9th planet in our solar system, a massive world orbiting far beyond Neptune. Now, Michael Brown is a particularly interesting figure in this story. He's the astronomer who discovered Eris, the dwarf planet whose discovery ultimately led to Pluto's demotion from planet status. Brown literally wrote a book called How I Killed Pluto and Why It Had It Coming. So when he comes forward claiming there's evidence for a new 9th planet, people pay attention. This isn't some fringe researcher making wild claims. This is a respected astronomer with a track record of major discoveries. Here's what Batygin and Brown found. They looked at 6 objects in the distant solar system, all with extremely elliptical orbits and all very far from Neptune's gravitational influence. These 6 objects all shared some strange characteristics. First, their orbits were all tilted roughly the same way relative to the plane of the solar system. Second, their perihelia, the closest points in their orbits to the Sun, all pointed in roughly the same direction. Third, the orientation of their orbits in 3-dimensional space was also similar. Now, you might think, okay, 6 objects isn't that many, maybe it's just a coincidence. But Batygin and Brown ran thousands of computer simulations to test this hypothesis. They calculated the probability that these 6 objects would end up with such similar orbital characteristics just by chance, no outside influence. The result? The odds were astronomically small, less than 0.3%. In other words, it was extremely unlikely to be a coincidence. So if it wasn't random chance, what was causing this clustering? Bodigan and Brown proposed that the gravitational influence of a large, undiscovered planet was shepherding these objects into similar orbits. They ran more simulations, testing different possible planets with different masses, different distances, and different orbital characteristics. And they found a solution that fit the data remarkably well. According to their calculations, there should be a planet roughly 5 to 10 times the mass of Earth, orbiting the Sun at a distance of about 400 to 800 astronomical units. To put that in perspective, Neptune orbits at 30 astronomical units from the Sun. This planet would be more than 13 times farther away than Neptune, in a region of space so dark and cold that the Sun would appear as little more than a bright star. The planet's orbit, according to their models, would be highly elliptical, taking it from roughly 200 astronomical units at its closest to as far as 1200 astronomical units at its most distant. It would take this planet somewhere between 10,000 and 20,000 years to complete a single orbit around the Sun. At that distance, with that orbital period, it's no wonder we haven't spotted it yet. But here's the really clever part. Bodigan and Brown's model didn't just explain the clustering of the 6 objects they originally studied. It also predicted where this planet should be in its orbit right now. And it explained several other strange features of the outer solar system that had puzzled astronomers for years. For example, there are some objects in the Kuiper belt with orbits tilted perpendicular to the plane of the solar system. These are called perpendicular objects, and nobody could explain how they got into such bizarre orbits. But when Bodigan and Brown included Planet 9 in their simulations, these perpendicular objects appeared naturally. The gravitational influence of Planet 9 over millions of years would gradually tilt some objects into these perpendicular orbits. Even more intriguingly, Planet 9 could explain why the Sun's axis of rotation is tilted slightly relative to the plane of the planet's orbits. This tilt has been a mystery for a long time, but if there's a massive planet out there with an orbit tilted relative to the solar system plane, its gravitational pull over billions of years could have gradually tilted the Sun's spin axis to its current position. The evidence was compelling, not proof, but certainly enough to get the astronomical community's attention. The paper caused a sensation. News outlets around the world ran stories about the possible 9th planet. Astronomers began planning observation campaigns to try to find it, and skeptics started examining the evidence, trying to poke holes in the theory. So if Planet 9 exists, why haven't we found it yet? The answer comes down to 3 main challenges: distance, size, and brightness. First, distance. At 400 to 800 astronomical units from the Sun, Planet 9 would be incredibly far away. Even at its closest approach, it would be about 13 times farther from the Sun than Neptune. Light from the Sun takes over 4 hours to reach Neptune. For Planet 9, that journey could take more than a day and a half, even at the speed of light. Second, while Planet 9 is predicted to be several times more massive than Earth, that doesn't necessarily mean it's physically huge. If it's an ice giant similar to Uranus or Neptune, it might be only slightly larger than Earth in terms of diameter. At such an immense distance, even a planet several times Earth's size would appear incredibly tiny through a telescope. Third, and most importantly, brightness. Planet 9 doesn't generate its own light. It's light. Like all planets, it would shine only by reflecting sunlight. But at such an enormous distance from the Sun, there's very little sunlight to reflect. The intensity of sunlight follows an inverse square law. At twice the distance, sunlight is 4 times dimmer. At 10 times the distance, it's 100 times dimmer. At 400 astronomical units, sunlight would be 160,000 times dimmer than it is here on Earth. Even with powerful telescopes, Planet 9 would be incredibly faint. Astronomers estimate it might have a magnitude of around 22 to 24. To give you a sense of scale, the human eye can see stars down to about magnitude 6 under perfect dark sky conditions. Each magnitude represents about a 2.5 times difference in brightness. Magnitude 24 is roughly 16 million times fainter than what you can see with your naked eye. You need some of the largest, most sophisticated telescopes in the world to detect objects that faint. And there's another problem. We don't know exactly where to look. Bottigan and Brown's models predict a general region where Planet 9 should be, but it's still a huge area of sky to search. Imagine trying to find a single dim light bulb somewhere in a completely dark city, and you only have a narrow flashlight beam to search with. That's essentially what astronomers are up against. Several major observation campaigns have been launched to try to find Planet 9. The Subaru telescope in Hawaii, one of the largest optical telescopes in the world, has dedicated significant observation time to scanning the predicted region. The Dark Energy Survey, while primarily focused on studying distant galaxies and dark energy, has also looked for signs of Planet 9 in its data. The Panoramic Survey Telescope and Rapid Response System, or PAN-STARRS, has been scanning the skies, cataloging moving objects that could potentially be Planet 9. These searches are painstaking. Astronomers take images of the same patch of sky over multiple nights or months, then compare the images, looking for anything that has moved. A distant planet would appear to move very slowly against the background stars, so you need long-time baselines to detect the motion. And you have to be careful to distinguish genuine distant planets from asteroids, Kuiper Belt objects, and artifacts in the data. So far, none of these searches have definitively found Planet 9, but that doesn't mean it's not there. Given the challenges of detection and the vast area of sky that needs to be searched, many astronomers argue that it's too early to rule out the planet's existence. The absence of evidence is not evidence of absence, as the saying goes. Moreover, some astronomers have proposed that Planet 9 might currently be in the farthest part of its orbit, where it would be dimmest and hardest to detect, or it might be located in a part of the sky that's difficult to observe, perhaps behind the plane of the Milky Way, where the dense star fields make it harder to spot faint objects. The search continues, with new data coming in all the time. But while we're looking for the planet itself, astronomers have also been studying the circumstantial evidence, looking at more distant objects to see if their orbits support or contradict the Planet 9 hypothesis. Since Bottigan and Brown published their original paper in 2016, astronomers have discovered several more distant objects with strange orbits, and many of them seem to support the Planet 9 hypothesis. One particularly interesting discovery came in 2018, when Scott Shepard, along with Chad Trujillo and David Tolan, announced the discovery of an object called 2015 TG387, nicknamed the Goblin because it was discovered around Halloween. The Goblin has one of the most extreme orbits of any known object in the solar system. At its closest, it's about 65 astronomical units from the Sun. At its farthest, it's over 2,000 astronomical units away. Its orbit is so detached from the rest of the solar system that Neptune and the other giant planets have essentially no influence on it whatsoever. The Goblin's orbit also shows the same clustering behavior that Bottigan and Brown identified. Its perihelion points in a similar direction to the other clustered objects, adding more weight to the idea that something massive is influencing these orbits. Another significant discovery was 2012 VP113, which I mentioned earlier. This object has an orbit that takes it out to about 440 astronomical units at its farthest point. Its orbital characteristics also fit the pattern predicted by the Planet 9 hypothesis. As more of these objects have been discovered, astronomers have been able to refine their statistical analyses. Some studies have found that the clustering becomes even more significant when you include additional objects. The probability that all these orbits would be aligned just by chance drops even further, making the case for Planet 9 stronger. However, not everyone is convinced. And that brings us to an important aspect of science, skepticism, and alternative explanations. Science works best when ideas are challenged and tested from every angle. And the Planet 9 hypothesis has certainly faced its share of challenges and alternative explanations. One major criticism is the argument goes like this: we've only discovered these distant objects because we happen to look in certain parts of the sky. Most sky surveys focus on the ecliptic plane, the region where most planets and Kuiper Belt objects orbit. But if we've been looking mostly in one direction, then of course we'll find most objects clustered in that direction. It's a selection effect, not evidence for a hidden planet. Some astronomers have run simulations testing this idea. They've tried to model what we would expect to see if there were observational biases, and whether that could explain the clustering. The results have been mixed. Some studies suggest that observational bias could account for at least some of the clustering. Others argue that even accounting for observational bias, the clustering is still statistically significant and requires an explanation like Planet 9. Another alternative explanation involves the collective gravitational influence of many smaller objects. Maybe instead of one large Planet 9, there are hundreds or thousands of smaller objects in the distant solar system, and their combined gravitational pull is creating the observed orbital clustering. This idea has some appeal because it doesn't require the direct existence of a single massive planet that we haven't found yet. However, this explanation has problems of its own. To create the observed effects, you'd need a tremendous amount of mass in the outer solar system, possibly as much as several Earth masses worth of small objects. That's a lot of material, and it's not clear how it would have gotten there or why we haven't detected more of these objects. Plus, computer simulations suggest that a bunch of smaller objects wouldn't create the same stable, long-lasting orbital clustering that we observe. The orbits would be more chaotic and less organized. A more exotic alternative involves primordial black holes. Some physicists have proposed that Planet 9 might not be a planet at all, but rather a small black hole, perhaps the size of a grapefruit, but with several times Earth's mass. Primordial black holes are theoretical objects that could have formed in the early universe, shortly after the Big Bang. If one of these primordial black holes happened to be captured by the sun's gravity billions of years ago, it could be lurking in the outer solar system, creating the gravitational effects we're attributing to Planet 9. This is a wild idea, and most astronomers are skeptical. For one thing, we have no direct evidence that primordial black holes of this size exist. For another, a black hole this small would be incredibly difficult to detect directly. It wouldn't emit light, and its gravitational lensing effects would be too small to easily observe. But the idea has captured some people's imaginations, and a few research groups have proposed novel ways to search for such an object, like looking for signs of dark matter annihilation around it. Another criticism of the Planet 9 hypothesis comes from the orbital characteristics themselves. Some astronomers have pointed out that the objects used in the original analysis have uncertainties in their orbital parameters. When you account for these uncertainties, the clustering might not be as tight as originally thought. Additionally, as more objects have been discovered, some don't fit the clustering pattern as well, which could suggest that the pattern is not as robust as initially believed. There's also the question of Planet 9's origin. If such a planet exists, how did it get there? Planets form from the disk of gas and dust that surrounds a young star. and that disk is usually concentrated near the star, not hundreds of astronomical units away. So where did Planet 9 come from? Several origin scenarios have been proposed. One idea is that Planet 9 formed closer to the Sun, perhaps in the region where the giant planets are now, but was gravitationally scattered outward by interactions with Jupiter or Saturn billions of years ago. Computer simulations show that this is possible. Young solar systems are chaotic places, with planets migrating and sometimes ejecting each other into different orbits. Planet 9 could be a casualty of this early chaos, flung into a distant orbit where it has remained ever since. Another possibility is that Planet 9 didn't form in our solar system at all. Instead, it might have been captured from another star system. In the early days of the solar system, the Sun was likely part of a cluster of young stars, all born from the same giant molecular cloud. These stars would have been relatively close together, close enough that planets could occasionally be transferred from one star to another through gravitational interactions. Planet 9 might be an exoplanet that used to orbit a different star, but ended up gravitationally bound to the Sun instead. A third scenario involves the Sun's original protoplanetary disk extending much farther out than we typically imagine. Maybe there was enough material in the outer reaches of the disk for a planet to form directly at a large distance from the Sun. This would require special conditions, but it's not impossible. Each of these origin scenarios has its own challenges and implications. But the point is that if Planet 9 exists, we need a plausible explanation for how it got there. And while several explanations exist, none of them are without problems. Let's imagine for a moment that Planet 9 is real and we eventually find it. What would this world actually look like? Based on the predicted mass, about 5 to 10 Earth masses, Planet 9 would likely be a type of planet called a mini Neptune or super Earth. These are categories of planets that don't exist in the inner solar system, but which we've discovered are extremely common around other stars. A super Earth is essentially a rocky planet larger than Earth but smaller than Neptune. A mini Neptune is a smaller version of the ice giants, Uranus and Neptune, with a rocky core surrounded by a thick atmosphere of hydrogen, helium, and ices. The distinction between these two types depends on the planet's composition, which in turn depends on how and where it formed. If Planet 9 is a mini Neptune, it probably has a core made of rock and ice, maybe a few times the mass of Earth, surrounded by a substantial envelope of gas. This gas would be composed primarily of hydrogen and helium, the most abundant elements in the universe, along with compounds like water, methane, and ammonia in their various forms. The planet's surface, if it has a defined surface at all, would be incredibly cold. At 400 to 800 astronomical units from the Sun, temperatures would be close to absolute zero, hovering just a few dozen degrees above the coldest temperature possible. At these temperatures, most gases would be frozen solid or liquid. Methane, which is a gas on Earth, would be a liquid or ice on Planet 9. Water would be hard as rock. The atmosphere, if thick enough, might have weather of sorts, though nothing like what we experience on Earth. With so little energy from the Sun, there wouldn't be much to drive atmospheric circulation. Instead, you might have slow, languid movements of gases, perhaps with bizarre clouds made of exotic ices forming and dissipating over centuries. The sky from Planet 9 would be a strange sight. The Sun would no longer appear as a bright disk, but rather as an incredibly bright star, far brighter than any other star in the sky, but still just a point of light. It wouldn't provide any significant heat or illumination. The landscape, if you were standing on the planet, would be lit primarily by starlight. The Milky Way would stretch across the sky, and on this dark, distant world, you'd be able to see more stars than you could possibly count. From this distance, Earth and the inner planets would be completely invisible without a powerful telescope. Even the giant planets would appear as faint points of light, Distinguishable from stars only by their slow motion against the background sky, the planet's orbit would give it a very strange year, taking somewhere between 10,000 and 20,000 Earth years to orbit the Sun. Once, Planet 9's seasons, if it has them, would last for millennia. But with such a distant, weak Sun, seasons wouldn't mean much. The planet would be frozen solid throughout its entire orbit, with only the slightest variation in temperature as it moves closer to or farther from the Sun. If Planet 9 has moons, which is quite possible for a planet of its size, they would orbit in the darkness, illuminated only by starlight and perhaps by reflected light from the planet itself. These moons could potentially be interesting worlds in their own right, possibly harboring subsurface oceans kept liquid by tidal heating, similar to what we suspect exists on Jupiter's moon, Europa, and Saturn's moon Enceladus. One fascinating aspect of Planet 9, if it exists, is that it would be a bridge between our solar system and interstellar space. It would spend most of its time in a region where the Sun's influence, while still dominant, is becoming comparable to the gravitational pull of the galaxy itself. In some sense, Planet 9 would be a citizen of two realms, still bound to the Sun, but living in conditions not too different from a rogue planet drifting alone between the stars. The discovery of Planet 9, if it happens, would be significant far beyond just adding another planet to the list. It would have profound implications for our understanding of planetary formation, solar system dynamics, and even the search for life beyond Earth. First, it would revolutionize our understanding of how solar systems form and evolve. The presence of a large planet in the outer solar system would tell us something important about the processes that shaped our planetary system billions of years ago. Whether Planet 9 formed where it is now, migrated there, or was captured from another star, each scenario would teach us something new about the early solar system and the mechanisms that govern planetary systems in general. Second, Planet 9 would affect our understanding of the outer solar system's structure. Its gravitational influence would have been shaping the orbits of comets, asteroids, and Kuiper Belt objects for billions of years. Understanding this influence would help us better predict where objects are and how they move, which has practical implications for things like asteroid impact predictions and future space exploration missions to the outer solar system. Third, the existence of super-Earths or mini-Neptunes is incredibly common around other stars. Observations from the Kepler Space Telescope and other exoplanet surveys have shown that these mid-sized planets are among the most abundant types in the galaxy. Yet our solar system, at least in its inner regions, doesn't have any. If Planet 9 exists and is indeed a super-Earth or mini-Neptune, it would be the only example of this planet type in our solar system, giving us a unique opportunity to study such a world up close. Understanding Planet 9 could help us interpret observations of exoplanets around other stars. We could send spacecraft to study it in detail, something we obviously can't do for planets light years away. We could analyze its atmosphere, study its interior structure, and learn about the processes that form and shape these types of worlds. Fourth, there are philosophical implications. For centuries, humanity has been grappling with our place in the cosmos. The discovery of new planets has repeatedly expanded our understanding of the solar system and, by extension, the universe. Finding Planet 9 would be a reminder that even in our own cosmic backyard, there are still mysteries waiting to be uncovered. It would show that the age of exploration and discovery is far from over. There's also the historical parallel to consider. Planet 9, if confirmed, would be the third planet discovered through mathematical prediction rather than direct observation, following Neptune and arguably Pluto, though Pluto's discovery was somewhat serendipitous. This would validate once again the power of mathematics and physics to reveal hidden truths about nature. It would be a triumph of theoretical science showing that we can use our understanding of gravity and orbital mechanics to deduce the existence of objects we've never seen. And as the search for Planet 9 continues, astronomers are not just relying on existing telescopes. New technology coming online in the next few years could dramatically improve our chances of finding this elusive world. One of the most promising tools is the Vera-C Rubin Observatory, previously known as the Large Synoptic Survey Telescope, or LSST. Located in Chile, this facility is designed to conduct the most comprehensive survey of the night sky ever attempted. Starting its operations in the mid-2020s, the Rubin Observatory will photograph the entire visible sky every few nights, creating a massive database of astronomical objects and tracking how they move over time. This capability is perfect for finding Planet 9. The observatory's large mirror and sensitive camera will be able to detect extremely faint objects, potentially down to magnitude 25 or fainter, and because it will be repeatedly imaging the same parts of the sky, it will be able to detect the slow movement of distant objects like Planet 9 against the background stars. Astronomers estimate that if Planet 9 is out there within the predicted range of distances and brightnesses, the Rubin Observatory should find it within the first year or two of operations. That's assuming it's in a part of the sky that the observatory can see from its location in Chile, and that it's not hidden behind the dense star fields of the Milky Way. Another technological approach: while Planet 9 would be very cold, it would still emit a tiny amount of infrared radiation, heat radiation, from its formation billions of years ago. Planets cool down over time, but large planets cool very slowly. Jupiter, for instance, still radiates more heat than it receives from the Sun, left over from its formation 4.6 billion years ago. Planet 9, being several times more massive than Earth, might also still have some residual heat. Infrared telescopes, like the James Webb Space Telescope or future infrared survey missions, might be able to detect this faint infrared glow. However, at the predicted distance, this would be an incredibly difficult observation, requiring very sensitive instruments and careful data analysis. There's also the possibility of detecting Planet 9 through its gravitational effects on spacecraft. Any spacecraft we send to the outer solar system experiences tiny accelerations from the gravitational pull of distant objects. If Planet 9 exists, it would create measurable perturbations in the trajectories of spacecraft, like Voyager 1 and Voyager 2, or the New Horizons probe that flew by Pluto. Scientists have analyzed the tracking data from these spacecraft, looking for anomalies that might indicate Planet 9's presence. So far, the results have been inconclusive. The spacecraft are so far from the Sun that there are many sources of uncertainty in their trajectories, and teasing out a signal from Planet 9 would require extremely precise measurements. But as these spacecraft continue their journeys into interstellar space, and as our tracking data improves, this method might eventually yield results. Some researchers have even proposed sending a dedicated mission to find Planet 9. This would be a spacecraft equipped with a powerful telescope sent to a location in space where it would have a better view of the outer solar system, perhaps from a different angle than we have from Earth. Such a mission could survey the region where Planet 9 is predicted to be, potentially spotting it more quickly than ground-based searches. However, such a mission would be expensive and would take many years to reach the optimal observation point. Given the uncertainty about Planet 9's existence, it's unlikely that space agencies would approve such a mission unless we have more concrete evidence first. More likely, such a mission would come after Planet 9 has been detected, serving to confirm its existence and begin detailed studies of its properties. The search for Planet 9 is an ongoing story, and there have been several interesting developments in recent years. In 2019, researchers at the University of Cambridge and the American University of Beirut published a study suggesting that Planet 9 might actually be smaller and closer than originally thought. Their analysis, using different computational methods and including more recently discovered objects, suggested that the planet might be around 5 Earth masses and orbiting at around 400 to 500 astronomical units. This would make it somewhat easier to find, though still incredibly challenging. In 2020, astronomers used data from the Atacama Large Millimeter Array, ALMA, to search for Planet 9 in the millimeter wavelength range. These observations can detect cold objects that don't emit much visible light, but do radiate slightly in longer wavelengths. The search didn't find Planet 9, but it did place some constraints on where it could be and how bright or warm it might be. Also in 2020, a study published in the Astronomical Journal by Kevin Napier, Larissa Marquardt, and others challenged the statistical significance of the orbital clustering. They argued that when you account for observational biases and uncertainties in orbital calculations, the clustering might not be as significant as originally claimed. This paper sparked significant debate in the astronomical community, with Batajian, Brown, and their colleagues defending their original analysis and arguing that the clustering remains statistically significant, even accounting for these effects. The debate continues, with papers being published on both sides of the argument. This is how science works, through a process of proposal, challenge, defense, and refinement. We gradually converge on the truth. In 2021, Michael Brown and Konstantin Batajian published a new paper examining additional evidence for Planet 9. They looked at the orbits of long-period comets, objects that take hundreds or thousands of years to orbit the Sun. They found that these comets also show some statistical anomalies that could be explained by Planet 9's gravitational influence. While not conclusive proof, this added another piece to the puzzle. More recently, in 2023 and 2024, additional trans-Neptunian objects have been discovered and catalogued. Each new discovery is analyzed to see whether it supports or contradicts the Planet 9 hypothesis. So far, the picture remains complex, with some objects fitting the prediction well and others less so. There have also been some humorous moments in the search. In 2023, an amateur astronomer using publicly available data from sky surveys thought they had found Planet 9. The excitement was short-lived, however, when professional astronomers analyzed the data and determined that the object was either a data artifact or a much closer and smaller object, possibly an asteroid. The incident highlighted both the promise and the challenges of citizen science in modern astronomy. The search for Planet 9 is an ongoing story, and there have been several interesting developments in recent years. In 2019, researchers at the University of Cambridge and the American University of Beirut published a study suggesting that Planet 9 might actually be smaller and closer than originally thought. Their analysis, using different computational methods and including more recently discovered objects, suggested that the planet might be around 5 Earth masses and orbiting at around 400 to 500 astronomical units. This would make it somewhat easier to find, though still incredibly challenging. In 2020, astronomers used data from the Atacama Large Millimeter Array, ALMA, to search for Planet 9 in the millimeter wavelength range. These observations can detect cold objects that don't emit much visible light, but do radiate slightly in longer wavelengths. The search didn't find Planet 9, but it did place some constraints on where it could be and how bright or warm it might be. Also in 2020, a study published in the Astronomical Journal by Kevin Napier, Larissa Marquardt, and others challenged the statistical significance of the orbital clustering. They argued that when you account for observational biases and uncertainties in orbital calculations, the clustering might not be as significant as originally claimed. This paper sparked significant debate in the astronomical community, with Battigan, Brown, and their colleagues defending their original analysis and arguing that the clustering remains statistically significant, even accounting for these effects. The debate continues, with papers being published on both sides of the argument. This is how science works, through a process of proposal, challenge, defense, and refinement. We gradually converge on the truth. In 2021, Michael Brown and Konstantin Batygin published a new paper examining additional evidence for Planet 9. They looked at the orbits of long-period comets, objects that take hundreds or thousands of years to orbit the Sun. They found that these comets also show some statistical anomalies that could be explained by Planet 9's gravitational influence. While not conclusive proof, this added another piece to the puzzle. More recently, in 2023 and 2024, additional trans-Neptunian objects have been discovered and catalogued. Each new discovery is analyzed to see whether it supports or contradicts the Planet 9 hypothesis. So far, the picture remains complex, with some objects fitting the prediction well and others less so. There have also been some humorous moments in the search. In 2023, an amateur astronomer using publicly available data from sky surveys thought they had found Planet 9. The excitement was short-lived, however, when professional astronomers analyzed the data and determined that the object was either a data artifact or a much closer and smaller object, possibly an asteroid. The incident highlighted both the promise and the challenges of citizen science in modern astronomy. There's also the fascinating possibility that AI might find Planet 9 in data we already have. Over the years, sky surveys have collected enormous archives of images. It's entirely possible that Planet 9 has already been photographed multiple times but hasn't been recognized as such in the data. It might appear in images from different surveys, too faint to stand out in any single image, but potentially detectable when multiple observations are combined. Data mining projects are specifically looking for this possibility. By combining data from different surveys, different telescopes, and different time periods, researchers hope to create a more complete picture of the outer solar system. If Planet 9 is hiding in this archival data, sophisticated algorithms and careful analysis might finally reveal it. The use of machine learning in astronomy is still relatively new, and there are challenges to overcome. AI systems can be biased by the data they're trained on, potentially missing unusual or unexpected objects. They can also generate false positives, identifying artifacts or noise as real objects. But as the technology improves, and as we gain more experience using these tools, they're becoming increasingly powerful aids in the search. Let's consider the possibility that after years of searching, we definitively determine that Planet 9 doesn't exist. What would that mean for astronomy and our understanding of the solar system? First, it wouldn't be a failure of science. Science progresses through hypotheses, testing, and refinement. The Planet 9 hypothesis was proposed based on real observations and sound reasoning. Testing this hypothesis, even if it ultimately proves incorrect, advances our knowledge. If Planet 9 doesn't exist, we'd still need to explain the orbital clustering and other anomalies in the outer solar system. This would push astronomers to develop alternative theories, perhaps leading to discoveries we haven't anticipated. Maybe we'd find that our understanding of gravity needs slight modifications at vast distances. Maybe we'd discover a population of medium-sized objects in the outer solar system that we haven't detected yet. Maybe there's some other force or effect shaping these orbits that we haven't considered. History is full of examples where the search for one thing led to the discovery of something else entirely. Percival Lowell's search for Planet X beyond Neptune was based on incorrect calculations about irregularities in Neptune's orbit. Clyde Tombaugh, continuing Lowell's search, did find Pluto, but it turned out to be far too small to be causing the supposed irregularities. Later, we learned the irregularities weren't real. They were measurement errors. But the search itself was valuable, leading to the discovery of Pluto and eventually to our understanding of the Kuiper Belt. Similarly, even if Planet 9 doesn't exist, the search for it is teaching us an enormous amount about the outer solar system. Every survey, every new object discovered, every analysis of orbital dynamics adds to our knowledge. We're mapping a region of space that was almost completely unknown just a few decades ago. There's also the possibility that something like Planet 9 exists, but is different from what we've predicted. Maybe it's farther away, or closer, or more massive, or less massive than expected. Maybe it's not a planet at all, but some other kind of object. The universe has surprised us before, and it will surprise us again. The search for Planet 9 is an ongoing story, and there have been several interesting developments in recent years. In 2019, researchers at the University of Cambridge and the American University of Beirut published a study suggesting that Planet 9 might actually be smaller and closer than originally thought. Their analysis, using different computational methods and including more recently discovered objects, suggested that the planet might be around 5 Earth masses and orbiting at around 400 to 500 astronomical units. This would make it somewhat easier to find, though still incredibly challenging. In 2020, astronomers used data from the Atacama Large Millimeter Array, ALMA, to search for Planet 9 in the millimeter wavelength range. These observations can detect cold objects that don't emit much visible light, but do radiate slightly in longer wavelengths. The search didn't find Planet 9, but it did place some constraints on where it could be and how bright or warm it might be. Also in 2020, a study published in the Astronomical Journal by Kevin Napier, Larissa Marquardt, and others challenged the statistical significance of the orbital clustering. They argued that when you account for observational biases and uncertainties in orbital calculations, the clustering might not be as significant as originally claimed. This paper sparked significant debate in the astronomical community, with Batajian, Brown, and their colleagues defending their original analysis and arguing that the clustering remains statistically significant, even accounting for these effects. The debate continues, with papers being published on both sides of the argument. This is how science works, through a process of proposal, challenge, defense, and refinement. We gradually converge on the truth. In 2021, Michael Brown and Konstantin Batygin published a new paper examining additional evidence for Planet 9. They looked at the orbits of long-period comets, objects that take hundreds or thousands of years to orbit the Sun. They found that these comets also show some statistical anomalies that could be explained by Planet 9's gravitational influence. While not conclusive proof, this added another piece to the puzzle. More recently, in 2023 and 2024, additional trans-Neptunian objects have been discovered and cataloged. Each new discovery is analyzed to see whether it supports or contradicts the Planet 9 hypothesis. So far, the picture remains complex, with some objects fitting the prediction well and others less so. There have also been some humorous moments in the search. In 2023, an amateur astronomer using publicly available data from sky surveys thought they had found Planet 9. The excitement was short-lived, however, when professional astronomers analyzed the data and determined that the object was either a data artifact or a much closer and smaller object, possibly an asteroid. The incident highlighted both the promise and the challenges of citizen science in modern astronomy, the Planet 9 hypothesis has captured public imagination in a way that many astronomical discoveries don't. There's something inherently exciting about the idea of an unknown world lurking in the darkness, a massive planet that has gone undetected until now. This excitement has spilled over into popular culture. Planet 9 has been mentioned in science fiction stories, appears in educational content, and has become a topic of speculation and debate online. Some people have even connected it to various predictions and prophecies, though these connections are not based on any scientific evidence. The cultural fascination with Planet 9 reflects a deeper human interest in exploration and discovery. We're drawn to mysteries, to the unknown, to the idea that there are still places to explore and things to find. In an era where much of Earth has been mapped and explored, where we can look up almost any fact instantly on the internet, the existence of an undiscovered planet in our own solar system is thrilling. This public interest is valuable for science. It creates opportunities for science communication, for engaging people with astronomy and planetary science. When people are excited about Planet 9, they're more likely to learn about orbital mechanics, about how telescopes work, about the history of astronomical discovery. They're more likely to support funding for telescopes and space missions. There's also been some confusion and misinformation, as often happens with popular science topics. Some people have confused Planet 9 with the discredited Planet X doomsday predictions that circulated online in the early 2000s. So, to be clear, Planet 9, if it exists, poses no danger to Earth. It's incredibly far away. Its orbit doesn't bring it anywhere near the inner solar system, and it has likely been in that orbit for billions of years without causing any problems. Astronomers and science communicators have worked to clarify these misconceptions while keeping the public engaged with the genuine scientific mystery. It's a delicate balance, maintaining excitement without overselling the hypothesis or misrepresenting the evidence. The search for Planet 9 is part of a broader effort to understand the outer reaches of our solar system. This region, once thought to be mostly empty, is now known to be full of interesting objects and dynamic processes. Looking forward, several missions and projects will contribute to our understanding of this region. NASA's New Horizons spacecraft, after its spectacular flyby of Pluto in 2015, continued into the Kuiper Belt, flying past an object called Arrokoth in 2019. The spacecraft is still functioning and continues to make observations as it travels deeper into the Kuiper Belt. While it's unlikely to directly observe Planet 9, its data on the environment and objects in this region is valuable. There have been proposals for dedicated missions to the outer solar system. One concept is an orbiter that would be sent to study Uranus or Neptune in detail, giving us our first close-up views of these ice giants, since Voyager 2 flew past them in the late 1980s. Such a mission would pass through regions where it might detect signs of Planet 9's influence, of small, fast probes that could be sent to intercept newly discovered Kuiper Belt objects, or even to search for Planet 9 directly. With advances in propulsion technology, including solar sails and nuclear electric propulsion, it might be possible to reach the outer solar system faster than previous missions. Ground-based observations will continue to improve as well. The next generation of extremely large telescopes, including the Giant Magellan Telescope, the 30-meter telescope, and the European Extremely Large Telescope, will have unprecedented light-gathering power and resolution. These telescopes will be able to detect fainter objects and study them in more detail than ever before. All of these efforts will contribute to solving the Planet 9 mystery, whether by finding the planet itself or by gathering enough data to definitively rule it out. The Planet 9 hypothesis has captured public imagination in a way that many astronomical discoveries don't. There's something inherently exciting about the idea of an unknown world lurking in the darkness, a massive planet that has gone undetected until now. This excitement has spilled over into popular culture. Planet 9 has been mentioned in science fiction stories, appears in educational content, and has become a topic of speculation and debate online. Some people have even connected it to various predictions and prophecies, though these connections are not based on any scientific evidence. The cultural fascination with Planet 9 reflects a deeper human interest in exploration and discovery. We're drawn to mysteries, to the unknown, to the idea that there are still places to explore and things to find. In an era where much of Earth has been mapped and explored, where we can look up almost any fact instantly on the internet, the existence of an undiscovered planet in our own solar system is thrilling. This public interest is valuable for science. It creates opportunities for science communication, for engaging people with astronomy and planetary science. When people are excited about Planet 9, they're more likely to learn about orbital mechanics, about how telescopes work, about the history of astronomical discovery. They're more likely to support funding for telescopes and space missions. There's also been some confusion and misinformation, as often happens with popular science topics. Some people have confused Planet 9 with the discredited Planet X doomsday predictions that circulated online in the early 2000s. So, to be clear, Planet 9, if it exists, poses no danger to Earth. It's incredibly far away. Its orbit doesn't bring it anywhere near the inner solar system, and it has likely been in that orbit for billions of years without causing any problems. Astronomers and science communicators have worked to clarify these misconceptions while keeping the public engaged with the genuine scientific mystery. It's a delicate balance, maintaining excitement without overselling the hypothesis or misrepresenting the evidence. The search for Planet 9 is part of a broader effort to understand the outer reaches of our solar system. This region, once thought to be mostly empty, is now known to be full of interesting objects and dynamic processes. Looking forward, several missions and projects will contribute to our understanding of this region. NASA's New Horizons spacecraft, after its spectacular flyby of Pluto in 2015, continued into the Kuiper Belt, flying past an object called Arrokoth in 2019. The spacecraft is still functioning and continues to make observations as it travels deeper into the Kuiper Belt. While it's unlikely to directly observe Planet 9, its data on the environment and objects in this region is valuable. There have been proposals for dedicated missions to the outer solar system. One concept is an orbiter that would be sent to study Uranus or Neptune in detail, giving us our first close-up views of these ice giants, since Voyager 2 flew past them in the late 1980s. Such a mission would pass through regions where it might detect signs of Planet 9's influence, of small, fast probes that could be sent to intercept newly discovered Kuiper Belt objects, or even to search for Planet 9 directly. With advances in propulsion technology, including solar sails and nuclear electric propulsion, it might be possible to reach the outer solar system faster than previous missions. Ground-based observations will continue to improve as well. The next generation of extremely large telescopes, including the Giant Magellan Telescope, the 30-meter telescope and the European Extremely Large Telescope, will have unprecedented light-gathering power and resolution. These telescopes will be able to detect fainter objects and study them in more detail than ever before. All of these efforts will contribute to solving the Planet 9 mystery, whether by finding the planet itself or by gathering enough data to definitively rule it out. One of the most common questions about Planet 9 is, when will we find it, or when will we know for sure if it doesn't exist? The answer depends on several factors. If Planet 9 exists and is near the brighter end of predicted brightness, and if it's currently in a region of sky that's being surveyed, it could be found within the next few years. The Rubin Observatory, beginning operations around 2025 or 2026, is expected to significantly accelerate the search. However, if Planet 9 is at the fainter end of predictions, or if it's currently behind the plane of the Milky Way where dense star fields make detection difficult, or if it's in a part of the orbit where it's farthest from the Sun and thus dimmest, it could take much longer to find. Some estimates suggest it might not be detected until the 2030s or even later. On the flip side, ruling out Planet 9's existence is also difficult. To definitively say it's not there, we need to survey essentially the entire sky to a certain depth, accounting for all the regions where it might be hiding. This comprehensive survey will take years, even with the most advanced telescopes. There's also the possibility of a middle ground. We might find something that's similar to the predicted Planet 9, but not exactly matching the predictions. For instance, we might find a planet that's slightly smaller or in a somewhat different orbit than predicted. Would that count as confirming the hypothesis? Or would it be considered a different discovery? Realistically, within the next decade, we'll likely have a much clearer picture. Either Planet 9 will be found, or the surveys will be comprehensive enough to place very tight constraints on where it could be and what its properties could be. Those constraints might become so restrictive that the hypothesis becomes untenable, or they might point to refinements in the prediction that lead to eventual discovery. The scientific process doesn't always give us immediate, definitive answers. Sometimes we have to be patient, to gather more data, to refine our methods. The search for Planet 9 is a reminder that science often works on timescales longer than a news cycle or a social media trend. The astronomers involved in the search for Planet 9 have devoted years of their careers to this mystery. Their perspectives offer insight into what drives scientific inquiry and how scientists think about unsolved problems. Michael Brown, who famously led the team that discovered Eris and many other dwarf planets, has said that finding Planet 9 would be redemption of sorts for killing Pluto. There's a poetic justice to the idea that the same astronomer who demoted Pluto might add a new ninth planet to take its place. In interviews, Brown has expressed both confidence and humility about the search. He's confident that the evidence for Planet 9 is strong, that something is causing the observed orbital clustering, but he's also humble enough to admit that science has been wrong before, that they might be missing something, that the universe might surprise them. Konstantin Batygin, Brown's colleague at Caltech, brings a theoretical perspective. He's fascinated by the dynamics, by how Planet 9's gravity would sculpt the orbits of distant objects over millions of years. For him, Planet 9 is a puzzle to be solved, a problem that exercises different aspects of orbital mechanics and gravitational theory. Both scientists have expressed how exciting it is to work on a problem where the answer isn't known. In many areas of science, researchers are filling in details, refining measurements, building on established knowledge. But with Planet 9, They're working at the frontier of the unknown. They could be completely right or completely wrong, and they won't know until the data comes in. Scott Shepard, another key figure in the search, has focused on discovering more distant objects, expanding the catalog of Neptunian objects that can be used to test the Planet 9 hypothesis. He's taken a more observational approach, believing that the best way to solve the mystery is to gather more data. Each new object discovered either supports or challenges the hypothesis, gradually narrowing down the possibilities. These scientists also acknowledge the contributions of others, including skeptics, who challenge their conclusions. Healthy debate is essential to science. It's through this process of proposal, challenge, and response that truth emerges. While most discussion of Planet 9 assumes it's a planet similar to Uranus or Neptune, but smaller, there are more exotic possibilities that have been considered. One intriguing idea is that Planet 9 could be a primordial black hole. As I mentioned earlier, these hypothetical objects of phase would have formed in the first moments after the Big Bang from regions of space that were slightly denser than average. Unlike black holes formed from dying stars, primordial black holes could have any mass from less than a kilogram to thousands of times the Sun's mass. A primordial black hole with several times Earth's mass would be incredibly tiny, smaller than a baseball, but with intense gravity. It wouldn't emit light, making it essentially invisible to traditional telescopes. However, it would have the same gravitational effects as a planet of the same mass, which means it could explain the orbital clustering just as well as a conventional planet. Detecting such an object would require creative approaches. One proposed method involves looking for gravitational lensing. When light from a distant star passes near a massive object, the object's gravity bends the light, potentially making the star appear briefly brighter, or creating multiple images. For a small black hole, this effect would be very subtle and brief, but potentially detectable with the right equipment. Another proposed detection method involves looking for signs of dark matter annihilation. If dark matter particles collide near the black hole's event horizon, they might annihilate, producing high-energy photons or other particles that could be detected. Several research teams have proposed using gamma-ray telescopes to look for this signal cell. However, most astronomers consider the primordial black hole explanation unlikely. We have no direct evidence that primordial black holes of this size exist, and the probability that one just happened to be captured by the Sun seems low. It's more likely that if something is causing the orbital anomalies, it's a conventional planet. Another alternative is that Planet 9 could be a rogue planet that was captured by the Sun. Rogue planets are worlds that don't orbit any star, instead drifting alone through the galaxy. They're thought to be fairly common, ejected from their original solar systems during chaotic early formation. If the Sun passed close to a rogue planet billions of years ago, it's possible that the planet could have been captured into a distant orbit. This scenario would explain some of Planet 9's unusual orbital characteristics. A captured planet would likely have an orbit tilted relative to the ecliptic plane, and with high eccentricity, exactly what's predicted for Planet 9. If this is the case, Planet 9 might be even more interesting than we thought. It could be a true alien world, formed in a completely different stellar system, offering a unique window into how planets form under different conditions. The Planet 9 saga also offers insights into how modern science works, the sociology of scientific communities, and how scientists communicate with each other and the public. When Batigan and Brown published their initial paper in 2016, they didn't just submit it to a journal, and wait for publication. They held a press conference, gave interviews, and actively engaged with the media. This was a deliberate choice. They believed their evidence was strong enough to warrant public attention. And they wanted to encourage other astronomers to join the search. This approach has both benefits and risks. On the positive side, it generates excitement and interest, potentially attracting more resources and attention to the problem. It encourages collaboration and ensures that multiple independent groups are working on the same question. On the negative side, it can create hype that outruns the evidence. And if the hypothesis eventually proves wrong, it can lead to public skepticism about science. The response from the astronomical community has been mixed. Some astronomers immediately joined the search, convinced by the evidence. Others were more skeptical, publishing papers that challenged the statistical analysis or proposed alternative explanations. A few criticized the publicity around the announcement, feeling that it was premature to generate so much public interest based on indirect evidence. This diversity of responses is actually healthy for science. No single perspective should dominate. Ideas need to be challenged and tested from multiple angles. The back and forth between proponents and skeptics, conducted through peer-reviewed papers and conference presentations, is how science refines its understanding. There's also been collaboration across institutions and countries. The search for Planet 9 involves astronomers from dozens of institutions around the world. Data is shared, methods are compared, and results are independently verified. This collaborative approach, facilitated by modern communication technology and data sharing practices, is increasingly how cutting-edge science gets done. At the same time, there's still competition. Multiple teams want the glory of being first to find Planet 9. This competition can drive as teams develop better methods and work more intensively to be the first to succeed. But it can also create pressure and occasionally lead to rushed or overhyped announcements. The way science is funded also plays a role. Securing telescope time on major facilities requires writing competitive proposals. Projects that are exciting and have the potential for major discoveries are more likely to be approved. Planet 9 fits this bill perfectly, which is why multiple observation campaigns have been approved. But this also means that researchers have incentives to present their work in the most exciting possible light, which can sometimes lead to overclaiming or oversimplification. On a practical level, the discovery of Planet 9 wouldn't immediately affect most people's daily lives. It's not going to change the weather, influence the economy, or alter our technology, but on a deeper level, it would matter in ways both subtle and profound. First, it would be a reminder of the power of human curiosity and ingenuity. We would have used mathematics, physics, and careful observation to find something invisible, to deduce the existence of a world billions of miles away, based purely on how it affects other objects. That's remarkable, and it's worth celebrating. Second, it would be educational. Imagine the classroom lessons, the documentaries, the books that would be written about Planet 9. An entire generation of students could learn about the solar system using Planet 9. As an example, understanding how scientists solve mysteries and push the boundaries of knowledge. Third, it would inspire future exploration. Once we know Planet 9 exists and where it is, plans could be made to send missions there. It would take decades for a spacecraft to reach Planet 9, but just the existence of such a goal would drive technological development and inspire engineers and scientists to solve the challenges. Fourth, it would contribute to our broader understanding of the universe. Every piece of knowledge about planetary systems, about how they form and evolve, helps us interpret observations of exoplanets around other stars. This, in turn, informs our understanding of how common habitable worlds might be. one of the fundamental questions in science. Fifth, it would be culturally significant. Major scientific discoveries become part of our shared human story. The discovery of America, the invention of the telescope, the theory of evolution, the structure of DNA, the landing on the moon, these are moments that define eras and inspire generations. Finding Planet 9 might not be as transformative as those examples, but it would still be a significant milestone in our exploration of the cosmos. And finally, it would simply be cool. We'd have a new world to imagine, to learn about, to wonder about. What does it look like? Does it have moons? Could we eventually send probes there to study it up close? These questions would captivate imaginations and remind us that we live in a universe full of wonders. So where does that leave us? After thousands of words exploring the mystery of Planet 9, what can we conclude? The evidence for Planet 9 is compelling, but not conclusive. There are statistical patterns in the orbits of distant solar system objects that are difficult to explain without invoking a large, undiscovered planet. Computer simulations show that such a planet could create exactly the patterns we observe, but we haven't actually seen the planet yet. And alternative explanations haven't been completely ruled out. The search continues with ever-improving technology and methods. New telescopes, new sky surveys, new data analysis techniques, and new discoveries of distant objects all contribute to solving the mystery. Within the next decade, we'll likely have a much clearer answer. One way or another, if Planet 9 is found, it will be a triumph of theoretical astronomy, a reminder that sometimes you can find things not by looking for them directly, but by studying their effects. It will open up new questions about the solar system's formation and evolution, and it will give us a unique opportunity to study a type of planet that is common in the galaxy, but absent from our Sun's family of worlds. If Planet 9 isn't found, if it turns out not to exist, that will also be scientifically valuable. It will mean we need to find other explanations for the observed phenomena, which could lead to new discoveries and new understanding. Either way, the process of searching has already taught us an enormous amount about the outer solar system. The Planet 9 mystery is a perfect example of science in action. And it shows how scientists generate hypotheses based on observations, test those hypotheses through multiple methods, debate and challenge each other's conclusions, and gradually converge on truth through this process. It shows that science isn't a collection of facts, but a method for understanding reality, a way of asking questions and seeking answers. It also reminds us that exploration and discovery are still possible in our own cosmic backyard. We often think of space exploration as being about distant galaxies or exoplanets, light years away. But right here in our solar system, at the edge of the sun's gravitational influence, there might be a massive world we've never seen, waiting to be discovered. Whether you're an astronomy enthusiast, a casual science fan, or just someone curious about the world around you, the Planet 9 story. It's unfolding right now in real time as astronomers around the world scan the skies and analyze data. Any day, any observation could be the one that finally reveals this hidden world or definitively rules out its existence. So keep an eye on the news from astronomy. Watch for announcements from the Vera Rubin Observatory when it comes online. Follow the scientists on social media as they share their latest findings. Follow these, and remember that out there, beyond Neptune, in the cold darkness at the edge of our solar system, there might be a massive planet, slowly orbiting, waiting for someone to finally spot its faint glimmer of reflected sunlight. That's the mystery of Planet 9. That's the adventure of modern astronomy. And that's why, even in an age where we can study galaxies billions of light years away, there are still profound mysteries right here at home. But thank you so much for watching this deep dive into Planet 9. If you enjoyed this video, please give it a thumbs up, share it with friends who might find it interesting, and subscribe to the channel for more explorations of space, science, and the mysteries of the universe. Leave a comment below telling me what you think. Does Planet 9 exist? Will we find it? What do you think it might be like? I'd love to hear your thoughts. Until next time, keep looking up, keep wondering, and keep exploring. The universe is full of mysteries, and who knows, maybe one of you watching this video right now will be the one to solve the mystery of Planet 9. Stranger things have happened in the history of science. Thanks for joining me on this journey to the edge of the solar system. See you in the next video.